Okay, yeah, thanks a lot for the invitation to speak at this nice conference. Yeah, the topic I'm speaking about today is something which is not exactly what I'm usually doing. So the history behind that choice of topic is that when I was invited to this conference, I thought, okay, out of the 4 topics in the title, I typically do quantum field theory and a bit of homotopy theory, but I never have encountered topological phases and also not so much operator algebras. So yeah, then I thought about what I will speak about, and I thought, yeah, I have to put something somehow in the middle that everybody understands me or nobody understands me. So I spoke with my friends, Marco Benini, Victor Carmona, who is around, and Peter Nikens, who left this morning. And we came up with kind of, I would say, a relatively basic story, but I find a nice story, and I hope you also find it a nice story. And this is the following. So we had a look at these superselection sectors and their use in topological order, and we tried to give a new, more geometric perspective on these things using techniques from prefactorization algebras. So I like to mix a bit between the different topics which this conference is supposed to represent. So the details you find in this paper, which is listed here. Okay, yeah, let me also start very much from scratch and say a few words about how I think about quantum systems and topological excitations, which they might carry or might not carry. So first, confusion is that I abuse notation all the time. When I say lattice quantum system, I don't necessarily need a lattice. I mean, I can take any discrete set. For what I'm going to do, let S be a discrete set, and you can think of it as the lattice as an example. And I call quantum systems defined on discrete sets lattice quantum. Okay, more precisely what I mean by that, I mean a lattice quantum system is for me a family of C-star algebras, one C-star algebra at every point of my discrete set. So here there's an AS at the point S, here's an AS prime at the point S prime. These algebras can be different. And they describe kind of the observables I can measure at these individual points. I have to say, for me, the lattice I think of as discretized spatial dimension. So it's some kind of a piece of matter somewhere sitting around. Now, on these algebras, I want to have a state, which I think of as a ground state of the system. And so this A of big S is the global algebra you can build by tensoring together and taking directed limits over these local algebras. So the state should be defined globally on the full thing. Okay, now some of these lattice quantum systems might have topological excitations, and these topological excitations are usually localized in certain regions of certain types. So those of you who followed up on Peter's lectures last week know that the typical excitations are kind of half strings, so they start at a point and extend string-like to infinity. So these types of excitations, they nicely live in cone-shaped regions. So, and these topological excitations, you can think of them as follows. So in this cone-shaped region, the state kind of differs from the vacuum state or from the ground state. However, outside it doesn't differ. So these are really excitations living inside a kind of fixed shaped region. Now, what I mean by topological, I have to say a bit more precisely. I will say that later way more precisely, but I say that now a bit more precisely first. So topologically kind of means loosely the following. So if my excitation now lives in that region, I mean, when it's a topological excitation, it should also be supportable in a smaller region. When I make this cone smaller, it should still fit in there. I mean, it's topological, it doesn't see size. Also, it should be somehow translation invariant, which means when I take that cone and I move it a bit around, I still should be able to localize my topological excitation in this shifted or translated regions. So in other words, so topologically here, of course, concerning these excitations means that they can be localized in any subset of the same shape, independently on if it's big or small or located here or there. I will formalize that in a moment a bit more.
Excuse me, just before we formalize, purely intuitively, like in 2 dimensions, the pictures here, bones are very simple, but in higher dimensions, cones can have pretty elaborate, say, bases, right?
Oh yeah, yeah.
So do we care what is the shape of the base? It will be very irregular.
What I'm saying is, I mean, I make then abstract categorical statements at some point, which means that yeah, it works for any shape you can think of. I'm not sure if they're good examples thereof, but the types of statements I'm after are I pick a choice of set S, I pick a choice of localization regions, and then I show something about that. I agree that, I mean, in higher dimensions, these localization regions can get quite tricky. And I have me not having much background in topological phases, I wouldn't even know what to look for in higher dimensions. So
take into dimensions.
What regions would you be interested in?
Well, if you take any subset, say, of a sphere, build a column.
Okay.
Build a column.
But it looks funny. It's kind of not a round cone. It's like a potato cone. Yeah, potato cones should work equally well, I think.
Wild. It would be very non-differentiable or something.
Okay, non-differentiable is not so good. I think this will hopefully clarify them later. So yeah, the shape of the region is very, very important and tells you at the end what type of algebraic structures you get. So the type of algebraic structures you find is pretty much related to the shape of regions you are localizing in. And I'm not 100% sure how wide one can go. But maybe one can go wide. I just didn't think about that. Peter told me cones are the things people take, and so I took cones as illustrating examples. Okay. So an interesting feature of some of these lattice models, for example, Kitaev's model, these toric code models, is that these topological excitations, when you package them all together, they assemble into a braided monoidal category. So you have tensor products, and then you can fuse these excitations, and you can braid them around and pick up non-trivial stuff. And this is what, at least from my limited point of view, makes these models interesting, because they naturally give rise to anyons, and hence you can think about applying them to quantum computation and other problems. So the goal of my talk is I want to tell you this story in a bit more conceptual and geometric way by combining techniques which I'm typically working on, namely algebraic quantum field theory, factorization algebras, and a bit of higher algebra. Now, so I want to tell you more about why or where this braided monoidal category emerges. Okay, as a first step, let me try to link these lattice quantum systems to AQFTs. This is something which, when you follow Peter's lectures, you will have heard a similar story about that, but I will say that now very quickly, very concisely, not quick. Okay, so remember, a lattice quantum system is just a family of C-star algebras, one at each point of your discrete set or lattice. Now we want to extend that to an AQFT. An AQFT is a kind of richer structure. It's a functor assigning to subsets of your discrete space S, C-star algebras. And this functor should kind of know about when things are disjoint. And here in this framework, it is as follows. If you have two regions, U1 and U2, sitting in a bigger region V, and they're disjoint, which is what I mean by this perp symbol, then you want that applying the functor to these inclusions, U1 into V, U2 into V, and then stuffing the result in the commutator gives 0. In simple words, the algebra elements coming from disjoint regions commute in bigger regions amongst each other. So that is roughly speaking that is an AQFT. So you have a functor satisfying this commutativity property. So it's kind of special types of functors. Okay, now this extension construction, you can make very precise how that works. And this is quite nicely, because I was first surprised. I was always a bit afraid about C-star algebras, because C-star algebras are not like, they're not algebras internal to some symmetric monoidal category that you can do operatic stuff and so on. But funny enough, a lot of these operatic techniques, which I probably have recognized that AQFTs described as functors satisfying this condition, when you know operat, you see immediately there's an operat giving these guys. Yeah? This is an operat produced out of the category here, out of the associative operat, and then some compatibility conditions, so some relations in there. So these operatic techniques, which are very useful, for example, to extend families of algebras to AQFTs, they kind of apply very nicely to this C-star algebraic situation. Because of a very special feature of the category of C-star algebras, it's a nice full subcategory of star algebras. And operatic techniques work nicely in star algebras, and they induce down to C-star algebras, because it's a nice subcategory. So this globalization or this kind of extension construction, you can nicely realize as a left-hand extension in this operatic case, where you extend from the set S to the category of all subsets of S. and this is here along the singleton subset inclusion. So even if you don't know about these practical ways how people extend AQFTs here, you kind of get a universal property and you know what you're dealing with. Okay. Now, because of the universal property you have, I mean, everything kind of boils down at the end to pointwise problems on the points of your lattice. And this also tells you that when you think about representations of this AQFT, you obtain the extension. These representation categories have a very concrete description. So by definition, the representation category of an AQFT is the representations of the global algebra or the global C-star algebra. So A of big S. But now, because A of big S is built universally from the small pieces, you see that these representations here are the same thing as families of representations of the pointwise algebra. So for every point, we have a representation of AS on the same Hilbert space, B of H. B of H here means bounded operators on the Hilbert space H. And these different pointwise representations, they have to kind of commute in the following sense. You take two different points, S and S prime. You go from the local algebras to the bounded operators, and what you get for different points produces commuting operators in Hilbert space. So this is what you get essentially from this commutation property you have in AQFT. Morphisms are bounded operators intertwining these families of representations. Okay, so this representation category here, this is where we later hunt for these excitations, these topological excitations. I want to find them in here. Now, even before talking about topological excitations, I already make a, if you know that stuff, quite standard observation, namely having a ground state, which is part of the datum you have for a lattice quantum system, your family of algebras and the ground state. Every state on a C-star algebra defines a representation. This is the usual GNS construction. So because the lattice quantum system comes with a ground state, this category of representations has a distinguished object I call pi 0. Pi 0 is the representation coming from omega 0, the ground state. Okay, so far everything still fine?
I have a question here at CMSA.
Yeah.
When you say a simple model for the representation, are you meaning for a representation C-star category? There could be many around, many choices around.
Of representation categories or of
relevant representation C-star categories.
Okay, here this is the category of all representations, which arguably is probably many of them are not nicely physical. So I will select you later. I will tell you on the next slide how to select from this big representation category, which doesn't have much structure at the end, but a lot of objects, a lot of representation, how to select interesting representations. This is the game one plays when one wants to identify these topological excitations. You take all representations, way too big, but then you select nice subcategories thereof, which then get interesting structure. Does that answer it?
Thank you. Yes.
Okay, thanks a lot. Yeah, so this representation category is way too big, yeah, and that will be now the topic on the next slide. And yeah, so the key buzzword which people use in order to describe kind of reducing from all possible crazy representations to nice representations, giving some meaningful stuff, is superselection sectors. And what I want to tell you on this slide is a bit about superselection sectors and how we can think of them as describing topological excitations. Okay, so superselection sectors is an old topic in algebraic quantum field theory, invented in the 70s by Topological, Haag, and Roberts. So these three gentlemen, they were back then interested in kind of finding charges or saying from an abstract point of view what are charges in particle physics, and they also looked for certain excitations of the vacuum state and wanted to interpret them as charges. So this has a long history with superselection sectors. However, more recently, Peter Nikens, he realized that the superselection sectors find nice applications to describe topological excitations in lattice quantum systems. So Peter kind of pioneered this application of DHR theory, so superselection theory, to lattice quantum systems. And the basic idea behind superselection sectors is quite simple. So let me try to get that as precise or as good as I can explain. Okay, so general representations are too wide. So we have to select special types of representations, which ideally kind of don't look too much different from the ground state. It's like the ground state and maybe a bit of stuff on it. And how do you describe ground state plus a bit stuff on it? Here's the formula. Okay, so I choose those representations pi, which are unitarily equivalent to the ground state. This is here this weakly equality sign. For all regions in a previously selected category of localization regions. Sorry, for all complements of regions of a previously selected. It's very hard to pass this sentence, isn't it? Okay, let me say it the other way. I choose my favorite shaped region, say cones. I choose a category of localization region, CS. And then I pick only those states which on the complement of all regions in CS are unitarily equivalent to the vacuum state. So here this condition enforces a lot of stuff. It kind of tells you that the difference between these representations and the vacuum or the ground state is just living in one of those regions U. Yeah, you can push that difference in a fixed region U, and you can also move it between different regions U. So this condition is quite nice. It tells you you can localize your excitations in the region U, and you can change the localization region. So it does multiple things in one shot. Okay, now let's just select those. In order to simplify the analysis, you see immediately, okay, I mean, that is true for all regions U in CS. So up to equivalence of categories, you can say, okay, now I fix my favorite region. I just hold one fixed. And then I can use the unitary, implementing the equivalence here, in order to make the equality strict for a fixed region U, but not for all. I can choose my favorite region and find an equivalent model of this category of superselection sectors where pi of a U complement is on the nose, pi 0 a U. Yeah, in these categories, I want to give names. I call them SSSU, superselection sectors, which are also strictly localized in a fixed region U. So these are the kind of categories I want to study. They are full subcategories of the representation, and they're way, way, way smaller. There's all sorts of crazy representations I'm kicking out here. The representations are just allowed to be locally in these localization regions different to the ground state. Okay, the first kind of pretty much obvious observation you see when you look at these things is, you see that when I have a region U and a bigger region U prime, there's always a kind of inclusion factor. SSS of U always lives in SSS of U prime. So these families of C-star categories labeled by localization regions, they give you a factor. I mean, they give you a factor on the category of localization regions going to C-star categories. And this factor, which is a consequence of this, I think Agnes yesterday called it movability or transportability. Because of this transportability which you build in here, this factor is locally constant, or which you can interpret as topological, in the sense that to every morphism in this localization region category, you assign a unitary equivalence. So in a hidden way, there is just one category, but I just prefer to distinguish this category in equivalent models attached to different regions. Yeah? So this is the kind of first observation. And I think that when you tell that story in this way, it kind of makes it transparent that when people say superselection sectors capture topological excitations, yes, I mean, this local constancy is exactly telling you about the topologicalness of your excitations. Yeah.
Does the morphism have to be a retract or really be like including into distant regions, for example? Would that be allowed?
In practice, these regions have the same shape, so they're all just cones. So this multiplicative structure coming from disjoint things is part of the next slide of the story. Yeah, so there will be more multiplicative structure. Here I just say think of fixed cones, and with this functor I can go from a small cone to a big cone and to a small cone somewhere else. So I can move things around. It's just moving around, but not multiplying anything. So it's just a category at the moment, no monoidal structure, no nothing. But as we move on, there will be more and more and more algebraic structures in these categories. So this is kind of the punchline I want to make. Okay, now, as already anticipated by Patrick, the thing is that, I mean, there are these configurations you can think about. Yeah, you can think of having a very big cone, which is the blue one here, which doesn't look like a cone anymore because my painting software wasn't big enough. So this should be a big cone here. So it's that whole upper region here. And in this big cone B, there is U1, U2, U3, U4 up to UN. So many small cones, but they're disjoint in there. So what I want to do next is I want to figure out a way how to take superselection sectors localized in these UIs and multiply them together to produce a superselection sector in this big region. Whenever these regions are disjoint. So I'm really insisting on the disjointness of these individual regions I'm multiplying it. So this is, for those of you who know about factorization algebras, this is kind of the key structure. You're allowed to multiply, but you have to multiply things which are disjoint. You cannot multiply stuff in the same region. So this is the kind of structure I'm after. I want to now find these factorization products or this multiplicative structure. I want to define them. Now, because of the pointwise description of these representations, it's pretty obvious what you can try to do. I mean, you have your pi 1, pi 2, pi whatever. Outside of these cone regions, it's always the ground state. So what kind of local representation I take on all these points which are not in the UIs is clear. I just take the ground state pi 0. So for all S in U1 complement cap, U2 complement cap, all the complements, I just put the ground state representation at this point. And when I am now taking a point in UI, I simply say, oh, I already have a pi I given here in that region. So I just take this representation here. So this is like the most naive thing you can write down. Yeah? Because of the pointwise description of these representations, this is the thing you can write down. And at the level of morphism, so like composed bounded operates just as they are. So this is the candidate I would like to turn into a factorization problem. Pointwise defined, piecewise defined representation. Now, the warning is that one has to be super careful because there is no reason whatsoever that the thing I'm defining here, pi 1 bullet up to pi n, that this is really a representation. Because remember that for representation, it's important that these different local representations at S and S prime for different S's and S primes commute with each other. That's key. That's important to have a representation of this A given. However, here nobody guarantees you that. Imagine I take pi 1 and pi 2 completely arbitrary. There's no reason why these things should commute at the level of the given space. So without any further hypothesis, this thing will not define at all a representation. So it starts from sectors and it produces something which is something it doesn't live in the desired replicative. So I have to think a bit and work a bit to make this guide work. And that turns out to be possible. The thing you need is some quite mild geometric hypothesis to make the story work, which are true for cones. Maybe this excludes your wild regions. One has to ensure that the geometric hypotheses I'm now listing are satisfied. And one analytical or algebraic hypothesis, which is standard in A50. So I need both a bit of geometric and a bit of algebraic hypothesis. And then I see that the kind of candidate factorization products I want to define are really well defined. Okay, let's go through the geometric ones. I always draw pictures to illustrate what's going on. Pictures of the cone shape in order to kind of match with the standard examples. Okay, these are assumptions about the category of localization. I want that for every U, for every localization region U, there exists another one V that is in the complement of U. So here you see there's a big cone U, but it still has a kind of gap here that in the complement of U I can squeeze in another cone V. So that is important to have that. The second hypothesis is a bit more sophisticated. I give you two localization regions, U and V. I want to find a smaller region V prime, such that U union V prime sits in another region W. So here the W I didn't draw, but the picture is as follows. You have here the U, here the V. They don't fit in a cone together. They're overlapping. They're covering the whole thing. But I can make the V smaller to go to that purple guy. And then this purple guy and the U sit in another cone. So you can, for example, cut out a small chunk, and then the complement gives you a cone for that. So this is also important, that you kind of can go small and then it fits eventually in some cone. And the last one is also something which you need in order to make this story work. For every region U and for every usually disjoint family you want to UN, you can make U smaller to some U prime, such that U prime intersects just at most one of these regions UI. Oof, that's getting already a bit wild, but here you see the picture, I think, illustrates it. If U1, U2, U1, U2 are disjoint, U intersects both of them. I don't want them to intersect both of them, but I can now follow along the cone U. Then there sits a smaller cone U prime in there, which just lies completely in U2. Can also happen that the cone is configured in a way that I can go further out, and then I'm not in any of the U1 or U2. So this is here the statement. U prime intersects UI at most for one index. Can also not intersect. Okay, so these are pretty harmless geometric hypotheses. I maybe have to add a comment. So those of you who know about superselection sectors and follow the work of Pennies, Dave Pennies and his friends and students, they wrote a quite nice paper where they also had geometric hypotheses under which superselection sectors form a braided monoidal category. So when you compare the geometric hypothesis I'm putting here, they're much, much weaker, because the thing I want to produce is something weaker than a braided monoidal category actually. So Pennies and his friends and colleagues, they found stronger hypotheses which even ensure you that you get a braided monoidal category at the end. So this I wanted to mention before I forget that. So that you have to implement, that you have to demand some geometric hypothesis to get some algebraic structure out that is not uncommon. So people doing these games, they find, depending on what they want to seed, they find they have to use different geometric hypotheses. Of course, all of them are true for cones, but it maybe limits how much wide one can deviate from cones. Yeah.
I don't understand. So you didn't show W. I'm not confused. What is W in the second picture?
The W would be that. So I take a small cone and I take the complement. So W has to contain V prime and U. So I'm taking this small cone and the complement. The complement is then the W. I have to draw it, sorry. It's a cone. Here, let me draw the cone U. Let me get them roughly the same shape. So the cone U is all down here. Then the cone V prime is that one, all in here. And then the cone this one here. Okay. W is the big guy outside. So I can produce a cone by kind of finding complement. Yeah.
Thank you.
Okay. Now the algebraic assumption is pretty standard for, at least for those who interacted with this AQFT approach to topological order. So what I have to assume is called Haag duality. But those of you who never heard Haag duality, was there a question? No. Those of you who never heard Haag duality, let me justify this condition here. So if I give you any region U, because of locality or commutativity encoded in an AQFT for disjoint regions, it's kind of obvious that the algebra on the complement of U, when you represent it, it commutes with the algebra on U. This is just the consequence of the commutativity built in an AQFT. So in other words, the pi naught of A of U complement lives in the commutant of pi naught AU. Now this inclusion, you apply another commutant to that, then you see that the bicommutant of AU, of pi 0 AU, lives in the commutant of pi 0 AU complement. Yeah? Just apply that here. And Haag duality is the assumption that this inclusion is in fact an equality. And that is technically quite useful because you want to know if something lives in a region or in the bicommutant of the algebra in that region, which is like a von Neumann algebra completion. And you often want to know, does my element, my operator live in that region? And the only practical way you have to check that is to show that the operator you're considering commutes with stuff in the complement of the region. But then you need Haag duality to say, when it commutes with everybody in the complement, it must live in the region. That is why it's kind of sensible to have equality here. So Haag duality is really allowing you to determine the localization of an operator by just checking with who it commutes. So that is the key checking. Yeah, so this is standard. I think also, and not really standard. I mean, people more analytically minded people, they have then approximate Haag duality or other forms of Haag duality. So these are weaker, as the name says, but I think it's fair to assume Haag duality. I think Peter and his students and collaborators, they proved Haag duality for the Tory code and other related models. So at least there's one example doing that. Okay. Long story short, let me tell you about the results here you can obtain. So if your category of localization region satisfies the geometric assumptions, and if your AQFT in the ground state satisfies Haag duality, then these candidate factorization products I was presenting on 2 slides before are indeed well defined, and they define a locally constant prefactorization algebra on the category of localization regions with values in C-star categories. So this PCS, this is how I denote the operands encoding prefactorization algebra. So that's simply my notation. CS is the category of localization regions. There's a kind of disjointness on it. You can say, okay, 2 regions are independent or disjoint when they're disjoint. And then you can produce a prefactorization operand out of that. So this is what you get. You get your superselection sectors fit into the structure of a prefactorization algebra, assigning C-star category. So that's a funny one. It kind of pushed you up one categorical level. You start from C-star algebras, you end up with C-star categories. So you categorified ones in a certain sense. And it's locally constant. And this locally constant is exactly the feature of the topologicalness of these excitations. It's the prefactorization algebra operand. So what I mean by that is, so CS is a category of certain regions. So PCS, it's an operand. So it has objects and it has operators. So what are the objects? The objects are just the localization. Now, what are the operations? Operations can be like in a category, but these are many to one operations, isn't it? And there exists exactly one operation if and only if ui is in V for all I and ui can uj with M. So in a way, this is the kind of the operand encoding these pictures which I was drawing before. So typically prefactorization algebras are defined on manifolds, but there is no problem in defining them on discrete sets or whatever. You just need some category of regions. You have to know when are 2 things independent, or we call that orthogonality relation, and then you produce an operand out of that. In that SSS, it says it's an algebra over that operand. So I assign to every region a C-star category. To every picture where many cones sit disjointly in a big cone, I assign a multiplication operation. And this composes associative. Appropriate sense. Okay, so that's nice. So it seemed that so these kind of things people are doing with superselection sectors naturally lead to a prefactorization algebra, even locally constant, witnessing the topologicalness of the problem. But that's not all. There's even more. I mean, the Haag duality comes with even more tricks and even more stuff. So Haag duality, when you again use this property all over and all over, you can see, oh, there's something special happening. If you have a superselection sector localized in some, what's special happening is of course well known in the AQFT community. It was just special for me to see that this is happening. So if you have a superselection sector localized in U, what you figure out is, it's okay. It defines in particular a representation of the algebra associated to U on the Hilbert space. But now you see that this representation factors in a funny way. It factors through the ground state representation, pi0, which I let here go to the bicommutant of the represented algebra. And then on this bicommutant, there's an endomorphism rho, and then you include entropy of H. So every representation kind of factorizes into the ground state, followed by some endomorphism on this von Neumann algebra completion thingy here. And that's quite cool. Why is that so? So it of course factorizes also uniquely. So you see that instead of thinking about representations in this sense, you can think of endomorphisms. But endomorphisms come with an obvious monoidal structure. You just compose them. Yeah. So there is hidden analytically, as a consequence of Haag duality, there is another layer of monoidal structure on each of these superselection sector categories localized in you.
There's a typo there. By not both. Both levels. The bottom row is by not.
There's also pi naught. This should be an. This is pi naught. This is pi naught. This should be an endomorphism. It should go from the represented algebra of U bicommutant into itself. Okay. The row should be an endomorphism. So that's the key, that this Haag duality allows you to go from representations to endomorphisms related to the vacuum representation or to the ground state. And that's now nice because these things you can compose, produce another level of monoidal structure. Okay, this construct is relatively standard in DHR theory. So it's not my result. These people knew it's the 70s. Anyhow, but the key thing is now when you combine that with the story we have up there and you check it a bit more, then you see, okay, I mean, this locally constant prefactorization algebra, which we build kind of geometrically, is compatible with this object-wise monoidal structure. In the following sense, you have a prefactorization algebra, again, locally constant, now taking not values in C-star categories, but in strict monoidal C-star categories. So you have one more level of multiplication. So we have prefactorization algebra structure, geometric type multiplications, and then these monoidal structures which have an analytic origin. So this is the thing you see. So you see a lot of algebraic structure popping up here. Yeah.
It's not slightly confused. You said it's not your result, but you still have to check that you get the right type of algebras, that every representation factors through homomorphism, right?
Yeah, these things are by these things they are locally normal. So there is some when you have a representation corresponding to a superselection sector, you see that this representation is locally normal in the sense that you can extend it to the weakly continuously to the bicommutant. So this is built in. So the superselection sectors are already of this type.
Okay, but this completed local algebras, that needs to be properly infinite von Neumann algebras, right? Properly infinite.
I don't know about von Neumann algebras at all. So what is your concern? I mean, what is true, and I mean, what I checked myself is that when you have a superselection sector, it's not a fully channel representation, it's a superselection sector. And I take the representation we have on some cone-like region here, that this factorizes in this way. So I think there's no subtlety here that goes through.
Can I ask a question from the CMSA side?
Sure.
Great. So I know you just said that you don't like, or you're not familiar with the Neumann algebras, so it might be an unfair question, but I'm wondering why you're working with C-star categories and not W-star categories, because your intertwiners are just defined to commute with lots of things, and so I would expect them to be W-star categories. I was wondering if that's like somehow the prefactorization structure necessitates C-star categories rather than W. It just seems like W-star categories would be the natural thing to write down. So
yeah, it's again, for me, C-star and W-star is the same. So I'm really analytically, I'm pretty ignorant. I really don't know. So if I would know probably what the W-star category is, probably it's true. I mean, I was happy when I understood C-star categories. Okay, in a moment there comes something which is potentially linked. I need at some point that C-star categories are a symmetric monoidal model category. I need that in.
okay. Thank you. That's
categories, I don't know. For W-star categories, I don't know. Okay, yeah, so yeah, I agree that a lot of things look pretty W-starry, but I'm absolute beginner in C and W and other stars. So sorry for my ignorance. Okay, but you get C-star and it's good. I mean, it has a norm and stuff. Okay. Okay, so these are in a way the main results we can prove. So from a lattice, let me say that in simple words, from a lattice quantum system, under some assumptions of geometric and analytic form, you produce a factorization algebra on the localization regions, taking values in strict monoidal C star categories. Okay, now, but I promised you at the beginning braided monoidal categories, and so you might now ask, that doesn't look much like a braided monoidal category. So where is that? Where's that now? Yeah, so the key point, those of you who are familiar with factorization algebras, either in quantum field theory or in topology, you will of course know what's going on, but I don't assume that everybody is familiar with that. So I'm trying to explain now in a basic way how you should expect the braided monoidal category to emerge. And then I give some more details. Okay, so the key point is that prefactorization algebras are super general. I mean, they describe quite general algebraic structure linked to different types of geometry. So you look in the Costello-Guillen books, they do Riemannian, complex geometric, topological. Then you look in the stuff I'm doing with some friends, then it's Lorentzian. So they exist in a lot of different geometric contexts, and they always have different properties. So they're super general things. However, in simple geometric context, these factorization algebra structures, which are quite rich, sometimes boil down to stuff you are already familiar with. And I think the key example here is, for a simple geometric context, is what can be simpler than locally constant prefactorization algebras on Rn. So topological stuff on Rn. And this problem you can study is, for example, contained in Lurie's book, that you see that locally constant prefactorization algebras on disks in Rn are the same thing as these En algebras, which you know from topology. These En algebras are I comment on that in a moment. I don't want to be too general. So you recognize factorization algebras in simple enough geometric situations as being equivalent to other things other people invented for other purposes. Now these En algebras, the thing is that this covers my braided monoidal category I want to find, isn't it? Because a braided monoidal category from this perspective is the same thing as an E2 algebra in categories. So if I want to find a braided monoidal category, I have to look carefully at the prefactorization algebras I produce, and I have to find somehow disks in R2. When I find disks in R2, then I can say, aha, there's a braided monoidal category attached to that thing. Now, why 2 dimensions is exactly braided monoidal is this small cartoon here in the corner you see. So in disks in R2, there's a big disk and you include 2 small disks. Yeah, this picture gives you a tensor product. Yeah, 2 in 1. You have a multiplication. But now you can move these disks, you can change their orders, and this is the braiding. Now, if you do that twice, you see that you loop one disk around the other, but the loop doesn't contract because the rule is no touch the region. Also, the homotopies are not allowed to touch the region. So you see immediately that 2 dimensions is kind of linked to braided monoidal categories. And 3 dimensions, so E3 algebras, are the symmetric monoidal categories, or it depends on how high your categories are. Okay, so this is the thing. You have to find somehow disks in Rn to explain or to see why people observe braided monoidal categories all the time. Okay, so the goal is now I focus on a simple geometric context, because here now when the geometric context is too crazy, I cannot expect to say anything, to compare the thing I produced with something familiar, because there is no name for that thing in familiar mathematics. So I take cones in Zn, I keep n flexible for the moment. Yeah? So cones in Zn, and I want to figure out if this locally constant prefactorization algebra I produced before, if that thing has a more familiar description in terms of something. Now here you see the notation changed a bit, and this is a warning here. So in order to make these arguments now, I need a bit of infinity categories and infinity operands, but nothing super scary. These things are quite standard in the sense that you can read them up in Lurie's book. So you don't have to, you can completely black box that and just do some small checks. Yeah, so it's nothing super sophisticated. Okay, so I need a few tools from infinity categories, infinity operands, but quite easy tools, relatively. And in order to connect this kind of language to the stuff I'm doing here is yeah, C star categories, it was shown by Dell'Ambrogio and Bunke that this is a nice symmetric monoidal model category. And so you can associate to that thing a symmetric monoidal infinity category, which you see this there as typical in this business, the notation changes a bit. It goes from, in my case, from bold to more curly. And I'm now making statements about this infinity categorical level. Now you might ask, yeah, but C star categories is like more like a two categorical object. Why do we do infinity categories? Yeah, because the thing I'm saying doesn't really depend on what you put here. So the stuff I'm saying now can be done in any symmetric monoidal infinity category as target. So this is why I prefer to make statements of infinity categorical nature, because maybe in some years' time somebody comes with a lattice model which assigns more like stacky stuff, not like normal C star algebras, but more like higher kind of things. And then these techniques are ready to run it through some machine to detect what are the algebraic structures.
What does words mean? Combinatorial, simplicial?
Oh, these are horrible technical words. So, simplicial means it's a simplically enriched category, and the simplicial structure is compatible with the model structure. These are technical words, but the key thing is that symmetric monoidal model category, this is the key. The rest is adjective. So symmetric monoidal is clear what that means. And model category means that you have in particular specification of what are weak equivalences in this context. Yeah, and then model category theory gives you tools to kind of deal with weak equivalences and treat them as they would be equivalences in the usual sense.
Can you tell us what the weak equivalences are in C star cat?
Yeah, these are unitary equivalences. So what does that mean is you have a functor going in one way, a functor going in the other way, star functor, and they are quasi-inverse to each other with natural transformations whose components are unitary. Now you study that, and this is in this Dell'Ambrogio paper. If you study that, you see this stuff doesn't matter. So it's just an order. You forget the C star structure. It's an ordinary equivalence of categories. Yeah. So you can detect equivalences in C star categories by forgetting that they are C star categories. Treat them as normal categories, and then it's an ordinary, fully faithful, essentially surjective functor. Yeah.
I have a question. So I thought that for the equivalency in factorization algebras, with this like kind of correlated property.
You mean descent property?
Yeah.
No, you don't need. I mean, the Weiss descent is not essential here for these questions. So the Weiss descent is essential when, I mean, here I'm really restricting myself on disks, not on. So I build on disks, and the higher arity disk inclusions, I'm not thinking of them as disjoint subsets. I'm thinking of them as higher arity operations in the opera. So there are different models. So you can also work with multi-disks and take a factorization opera over multi-disks. And then you need Weiss descent probably to link those stuff. So there is a bit of different conventions of what is a prefactorization algebra opera. For me, it's always geometrically simple things, like here in this case, disks. And the disjointness comes through higher arity operations.
Just where does simplicial enrichment come from? Is it some trivial property? What is
this thing? So you don't need that to produce a symmetric monoidal infinity category. Okay. Yeah, but it helps you to do homotopy theory with these model categories. Okay. Yeah. Or I can tell you that more. So you can forget combinatorial and simplicial. I think symmetric monoidal model category is enough to produce a good symmetric monoidal infinity category. So I don't even know why I wrote that down. I just copy pasted it from the paper. So, and I should have suppressed the noise. These are technical properties which help you to do model category theory if you want so, but they are inessential here because I'm pushing stuff to infinity categories and ignore that.
One more technical question here. I'm sorry, I know you want to. The symmetric monoidal structure, C stars have a lot of different tensor products. Are you using tensor max or tensor min? Or...
Yeah, it is the maximal tensor.
Okay.
The maximal.
And could you possibly tell us some examples of definitions of what cofibrations or fibrations or
they are very
whichever the most interesting?
Yeah, so the model structure on C star categories is very similar to the one on categories. So what does that mean? Vibrations are isovibrations. These are things
Okay.
which these kind of relative basic lifting properties, and covibrations are, I think, just functors which are injective on objects or so.
Thank you very much.
So they're super concrete.
Yes.
It's really very concrete. Okay. Now I think I have to speed up a bit, but yeah, okay. So now let me sketch you a bit how this algebraic structure can now be identified. So I have to explain somehow how from cones in Zn and unit associative algebra, how does from these two things come something like disks in Rn? How does that function? The first kind of step is I want to get rid of the Zn and I want to trade cones in Zn with something different. But there's a kind of obvious way how you can do that. So you specialize to the category of cones which emerge from zero. So these are cones whose apex sits at the origin of your lattice. Okay. Of course, cones centered at zero sit inside all cones. So you have this left pointing inclusion functor of operands. When you have cones localized at zero, you can geometrically intersect them with the unit sphere around zero. So you can assign to every cone, you can assign a disk in the unit sphere. So this kind of gives you a zigzag relating between cones in Zn and disks in Sn-1. So it reduces dimension by one, which is kind of clear because cones eat up one dimension because they extend in the radial dimension. And it kind of gives you some link between cones in Zn and disks in Sn-1. So if you now take these operand maps and induce the pullback functors at the category of algebras over these operands, you see that you can go from locally constant prefactorization algebras on cones to locally constant prefactorization algebras on origin-centered cones. Here, this is just restrict. And you can go from disks to cones, just kind of doing that. And the funny thing is that the cones at zero and this at S-1, this left pointing arrow is an equivalence. So this is a small check you have to do, and this is why you have to look for collaborators like Victor, who knows that stuff and who can do these checks. So there is a small topological check you have to do, and you see that this thing here is an equivalence. So that means that I can go from cones at Zn to cones at zero, cones localized at zero, to disks in Sn-1. Yeah. So I can do these steps. Now, the unitary associative algebras, we can also geometrically kind of interpret or get rid of or trade them for something geometric. Here you just use Lurie's result that unitary associative algebras are the same as locally constant prefactorization algebras on the line, on disks in the line. So if you now package these things together, you see that you can go from the left-hand side here, which is where our superselection sectors live. So locally constant prefactorization algebras on cones in Zn, taking values in monoidal categories. You can run these two steps together, and you end up at locally constant prefactorization algebras defined on disks in the cylinder. Yeah? These are just these geometric arguments I'm doing here. You put them together. You can trade cones and monoidal structure with disks in a cylinder. And here I forgot to mention, you also need some additivity property, but this additivity property is not the sophisticated one which Claudia Scheinbauer and so on proved recently. This is an additivity property, a more basic one, which is already in Lurie's book. So this works pretty well here. Because you have to kind of, for this iterated prefactorization algebras, you have to kind of see that this corresponds to taking the product manifold. But this works here. Okay. So long story short, when you look at cones in Zn as your localization regions, the locally constant prefactorization algebra of superselection sectors has an underlying locally constant prefactorization algebra, which is defined on disks in the cylinder, R1 times Sn-1. And the sphere, from this picture, you see this arises geometrically as the angular coordinates of cones. But the origin of the line is more mysterious because this is from this additional monoidal structure, which was due to Haag duality. So I like to think of this line as something kind of an extra dimension emerging from the analytical structure you have in the game. So some of your geometric structure is geometric and some of them originates from analysis, which is quite fancy, I think. anyhow, so this almost looks like Rn. We almost find braided monoidal category, but not yet quite. Super late, sorry. I have to make a quick side remark here. This is indeed an equivalent perspective. This other way around pointing functor from cones to cones centered at 0 is also an equivalence of infinity categories. But that is not so easy to prove, and Victor Carmona worked out a proof, and this was so technical that we said, yeah, for telling our story, we accept that this might be forgetful and don't claim it's not forgetful. So if you work hard enough, you can also show that this is not forgetful, it's an equivalence. So the prefactorization algebra you produce on cones is really equivalently described by a prefactorization algebra on the cylinder. Okay. Now identifying, so we are almost there. I mean, when you have an n-1 sphere and you remove a point, then you get an Rn-1. Yeah, that's clear. So this geometric trick of removing a point, you can interpret here as well. I mean, when you have disks in Rn, they include into disks in the cylinder. So you can forget a level further to go from the cylinder to Rn, and then recover your En algebra. So in a way, the cylinder faithfully captures the structure we are after, and to see the usual En algebra or En monoidal category, you have to remove a point. So this is the punch. So for cones in Zn, you can, our locally constant PFA of superselection sectors has an underlying En monoidal C-star category. This is the thing what people want to see, because in 2 dimensions, on the 2-dimensional lattice, you get the braided monoidal C-star category, which people want to see. So quick comments. So this is clearly forgetful. I mean, removing a point with the sphere, you destroy the topology of the sphere, so you forget something. And what you forget are kind of homotopy groups of the cylinder, which also operate on this category in some funky way. So these homotopy groups of the cylinder, they give you additional algebraic structure on this En monoidal category. So for example, in 2 dimensions, there is another algebraic structure coming geometrically on these superselection sector categories. And this is the form of a self-equivalence, a braided monoidal self-equivalence, which you can geometrically think of as you have cones and you turn them once around the origin. So you kind of can pick up winding information when doing so. So I think this, I've not seen people in the literature realizing that, but just because of the geometry of cones, and that cones in 2D are kind of related to intervals in S1, there is this braided monoidal self-equivalence on the category of superselections.
So once extra structure imposes ribbon structure. Is this related to ribbon structure?
This one I don't think is related to ribbon structure. I wouldn't know how to get ribbon structure. But I'm using frame stuff. Probably. Yeah, when okay, exactly. You would have to put some group actions here in the game and then check to, and then maybe I will think about that.
Just ribbon structure gives you so like a spin for onions, which has to do with precisely what happens if you rotate the to palm.
I see. Oh, maybe these are indirectly linked. I don't know. I was maybe more naively thinking here about something like a holonomy you can do it and pick up some. Yeah, but as you say, I mean, it's maybe some phase or some stuff you can pick up by rotating it once. Yeah, maybe it's related. I don't know. Didn't think about that.
So in the Boolean case, precisely just extra structure is refines the quadratic function of the Boolean group, and the values of the function precisely with the spin.
Okay. Yeah, I didn't notice these connections, but it sounds interesting. Yeah. Thanks. Okay. Do I have 1 more minute to show my concluding remarks? Okay, so I do very few concluding remarks, just 3 of them. Number 1, so yeah, the story I told you about how to link superselection sectors to factorization algebras and how I think this clarifies the way how this algebraic structure emerges. I think that's a nice story, because at least for me it clarified a lot of things, but this is kind of a personal taste stuff. If you don't like prefactorization algebras, then maybe this confuses more. I liked it. I hope some of you will see. So the key advantage, so often people ask, so when you do something different, so what is the key advantage? And I think when I have to put in one bullet point, the key advantage is the following. So in the traditional picture, you're handling for braided monoidal categories. So you're kind of automatically restricted to very special geometric situations. For example, cones in set 2, where you expect the braided monoidal category to show up. This prefactorization algebra perspective is much more general. You can play that on any kind of category of localization regions subject to mild geometric conditions. And you get some algebraic structure on your categories of topological excitations. Let it be what they are. I mean, they are just, they have a prefactorization algebra structure, locally constant. If that is now corresponding to something you previously know or not, this can be explored. But my point is that you can predict, depending on the geometry, which kind of algebraic structure to expect. And you can predict that even precisely. I mean, fix your favorite discrete space, fix your category of localization regions. The algebraic structure you find on superselection sectors or topological excitations is this infinity localization of the prefactorization opera at all maps. Okay. And that is something you can in principle determine. It's not an easy problem, but something determinable. And so I think this question here, are there any interesting examples arising from condensed matter physics? I don't know. I mean, I just have seen cones and stuff. But yesterday in Agnes talk, which was quite nice, there were not only cones, there were also other kind of shapes. So maybe in the future, in these topological phases business, people come up with new shapes of regions. And I think running them through this prefactorization algebra picture allows you to predict which kind of algebraic structure to find. So I think that is nice for that. It's somehow predictive in a certain sense. Okay, thanks a lot.